Lesson 6.5, Simple Machines. Simple machines, they're things that make work easier. They don't change the amount of work that's done, but they do change the force required to do work. So work is force times distance. The amount of work stays the same, so that means that our force times our distances would have to stay the same. So what's going to happen is if I decrease the force, then I'm going to have to increase the distance. So a simple machine changes our work to have less force, but over a longer distance. Mechanical advantage is a measure of this, changing the force. It's the ratio of how much the simple machine multiplies the effort force into the resistance force required to do the work. So mechanical advantage is the resistance force over the effort force. But because the total work is the same, we can turn this into a ratio. Ideal mechanical advantage would be resistance force over effort force, which would equal effort distance over resistance distance. Notice the R's and the E's have flipped places, because the F and the D are inversely proportional to each other. The first simple machine is the lever. So we have a long arm, and there's a rotation point called the fulcrum. And there's this lever arm. So ideal mechanical advantage is going to be the effort lever arm divided by the resistance lever arm. So you're pushing down here, and your load that you're trying to move is there. The second simple machine is the wheel and axle. But it's actually a lever whose effort arm can rotate completely around the fulcrum. So our axle would be like the fulcrum. And so if this is our resistance, then the little r is our resistance distance, and the capital R is the effort distance. So dE, effort distance, is the radius of the wheel. dr, the resistance distance, is the radius of the axle. So your ideal mechanical advantage is the radius of the wheel divided by the radius of the axle. The next simple machine is the inclined plane, which is a sloped surface such as a ramp. The effort distance would be the length, so that's how far you have to push it with the force. The resistance distance is the height, so this replaces going straight up with going up on a slant. Takes less force, but it's over a longer distance. So the ideal mechanical advantage is the length over the height. A closely related simple machine is the wedge, which are two inclined planes put together. So our effort distance is the length, and the resistance distance is the thickness. So that goes into a crack and is pushed into the crack to push the two pieces apart, like an axe head or a knife, something like that. Ideal mechanical advantage is the length divided by the thickness. The fifth simple machine is the screw, which is really an inclined plane wrapped around a wheel and axle. So it's really a combination of two of the other simple machines. We have a lever attached to a circular inclined plane, is what it comes down to. The effort distance would be the circumference of the screwdriver, because you're applying a force in a circle. So the distance that's applied is the circumference of that circle. So it'd be like the circumference of the screwdriver handle. We'll call that 2 pi L, where L is the radius of the screwdriver. The resistance distance is the distance between the threads. We call that pitch, or P. So our ideal mechanical advantage is 2 pi L over P. The last simple machine is the pulley, which is a rope wrapped around a wheel and axle. The wheel and axle is a lever, so it's rope with a lever. The effort distance is the distance the rope is pulled. The resistance distance is the distance the weight is lifted. So in this first case, we're just pulling it once around, and those are the same. The mechanical advantage is 1. But I've added a second rope here in the second picture. So now every time we lift up a certain distance on the rope, the pulley only goes up half the distance because that distance gets split over 2 ropes. Our mechanical advantage turns out to be the number of ropes supporting the weight. So the first case N is 1. The second case with the 2 ropes, it's 2. This block and tackle, it's actually 4 ropes supporting the weight. So you can use this big block and tackle system, and you can, with a small amount of force, lift very heavy objects, but it requires pulling a long distance of rope. So remember, as the force goes down, the distance goes up. Find the ideal mechanical advantage of a ramp with length 10 meters and height 3 meters. Well, a ramp is an inclined plane, and the ideal mechanical advantage of an inclined plane is the length over the height. So it'd be 10 meters over 3 meters, which is 3.33. And there's no units because the meters canceled out. How about the ideal mechanical advantage of a 3-meter lever whose fulcrum is 50 centimeters from one end with a load? All right, let's draw a picture. The lever is 3 meters. This distance is 50 centimeters, or half a meter. So actually this distance over here is going to be 2.5 meters. So this is the effort, this is the resistance. For a lever, the ideal mechanical advantage is the effort over the resistance. So it'll be 2.5 meters over 0.5 meters, which is 5. Mechanical advantage of 5. What's the ideal mechanical advantage of a pulley that is supporting the load by 4 ropes? Well, the ideal mechanical advantage is the number of ropes supporting the load, so it's just 4. Oh, I know that one was difficult. How much rope needs to be pulled to lift the load 2 meters? Oh. Well, the ideal mechanical advantage is the effort distance over the resistance distance. So if our mechanical advantage is 4, we're looking for the effort distance. The resistance distance is 2 meters because that's how far we're lifting the load. So multiply, you get 8 meters for the effort distance. You need to pull 8 meters of rope to lift the load 2 meters. If the load's mass is 120 kilograms, how much force is required to lift the load? Well, mechanical advantage is the resistance force over the effort force. Now, our resistance force is going to be our weight, which is mg, so that would be 120 kilograms times 9.8 meters per second squared. We're assuming we're doing this on Earth, I guess. Which would be 1176 newtons. Our mechanical advantage is 4, and that's our resistance. Oh, well, how are we going to solve this? Multiply by the Fe. And then divide by the 4. If I divide by 4, we get 294 newtons. That's doable. Efficiency. The useful energy output is always less than the energy or work input. Why? Because some energy is lost to friction and heat, etc. So our efficiency is the useful energy or work output over the total energy or work input times 100%, make it a percent. Or work out over work in times 100%. All right, let's say the actual efficiency of a screw is 94%. The screwdriver handle has a radius of 1.25 centimeters, and the screw has a pitch of 1 millimeter, and a radius of 1.2 millimeters. If it takes 9 newtons of force on the screwdriver to screw it in, what is the frictional force resisting the screw? Well, let's see. Let's start with the ideal mechanical advantage of this. So it's 2 pi L over P, where L is the radius of the screwdriver handle and P is the pitch. So the radius of the screwdriver handle is 1.25 centimeters. Our pitch is 1 millimeter. But I need it in the same unit, so how about 0.1 centimeters? So that gives us 25 pi. So now let's find the ideal resistive force. So the mechanical advantage is the resistive force over the effort force. The resistive force is what we're looking for. Mechanical advantage is 25 pi. Effort force, it says, was 9 newtons. So I multiply by 9. I get 225 pi newtons for my resistive force. Okay, let's keep going. Let's find the effort distance. The effort distance would be how far we turn something, which would be the circumference of the screwdriver. The radius of the screwdriver handle was 1.25 centimeters. This time I do want it in meters. So change it to meters. And I get 0.025 pi meters. All right, we also need the resistance distance. All right, the resistance distance is just our pitch, which it says was 1 millimeter. So it's 0.001 meters. All right, now let's find the actual resistance distance. All right, using our efficiency. Our efficiency is the work out over the work in times 100%. So the work out, that is our resistance force times the resistance distance. The work in is the effort force times the effort distance. Divide by the 100%. Take the 0.001 divided by the 9 times the 25 pi. We get 0.00141 per Newton times FR. So we divide and we get 664 newtons for our resistive force. So our friction would be the difference. Our ideal resistive force was that, and this was the real. So we're going to take ideal minus the real. So 225 pi newtons minus 664 newtons is going to give us 42.4 newtons for the force of friction.